think we're still missing 2 people, so we can wait for a minute or two. 3 people maybe. By the way, if I just wrote something and you'd like to, for people in the wrong section would like to write it, and you see me there where I move, and then the camera follows me, just tell me to go and stand there again. Okay. I think we have a few people still missing, so I think I have a few people still missing. Yeah. Should I start? Okay. So this morning wasn't easy, I think, at least for some of you. It is not easy stuff, renormalization group. And technicalities aside, I do hope at least you appreciate a little bit that the phenomenon or the activity of resummation, of renormalization, and the arbitrariness you get does get you information, does give you consistency equations, differential equations, on acting on renormalized quantities, the ones you want to have, and that you can solve those to get some interesting new information. The technicalities of that are for you to maybe work with and to study again and go through the text. My experience tells me that this is not something that you should understand in one go, and that's okay, that's it. You have to work with it again and solve some problems with it, to slowly get some kind of feeling that yes, you have active control over the material. But you can, there's always, even for me still, room for leaving yourself confused. So don't worry about that. That's part of the game and also part of the fun. If you're looking for exact knowledge and complete, then maybe mathematics is a bit more of a thing. So what the previous analysis of this morning has shown is a bit of a meaning also of this beta function and anomalous dimensions, things you get when you do renormalization. And they really tell you some basic properties of a theory. And if you know them, you can get all order information. If you know them to 1 or 2 loops, just a finite order calculation, plus these RG equations or beta function equations, gives you all order information. So our previous analyses are our renormalization analyses have so far been one loop. What about higher loops? And here I will only say a little bit. The first thing you can say is hard, right? If you really want to do a full story, that proves to all orders are hard. They have been done for QED. You can find them in books, for QCD in lecture notes, perhaps in some books too. This is not easy. A lot of structure isn't there. I know for not even that long ago, maybe 10 years ago, a German mathematical physicist, Kreimer, has found this evidence for, if you look at the pattern of high order terms and the counter terms, if you construct these counter terms to very high order, evidence for Hopf algebra structures. And so you can find some surprising mathematical structures in these higher order terms. So what we like to do is at least do some naive power counting. So do something called UV power counting. Can we at least get a rough estimate of whether a diagram is UV divergent or not? But in the most general sense, and maybe some of you have seen this, it's kind of a fun little analysis with a surprisingly nice outcome. So let's look at the general graph G. And let me draw a general graph. I will certainly not compute it, not even for all the money in the world. I don't even think I could. So this is a nice complicated graph. Okay, 3 loops, etc. Lots of internal lines. So let me define some quantities. I'm doing this here also because when we start looking at the infrared case, tools such as these come in. I will not go there in the great detail, but it will be more complicated there. But the same idea. So define L as the number of loops. NB as the number of internal boson lines, and that NF as the number of internal fermion lines. What else do we need? G3 is the number of 3 gluon vertices. G4 will be the number of 4 gluon vertices. Psi will be the number of Q bar QG vertices. I need 2 more definitions. So EB is the number of external boson lines. And EF, well, you can guess, number of external fermion lines. And I think we're almost there. V is the total number of vertices. So lots of things to define. So you just categorize structures in this diagram without actually computing it. So let's see if we can make some statements about it. And the rest I'll leave as a tutorial question for the afternoon. So what is the degree of divergence of this diagram? Well, let's first actually inspect the diagram and put some numbers here. So you can help me out. How many loops do we have here? 3 loops. What is the number of internal boson lines? 4, right? 1, 2, 3, 4. Number of internal fermion lines? 1, 2, 3, 4, 5, 6, 7. Yeah. Number of 3 gluon vertices? 1. Number of 4-point vertices? 0. Number of fermionic vertices? How many? 8. Yeah, that's right. So we have 1, 2, 3, 4, 5, 6, 7, 8. Number of external boson lines is 3. Number of external fermion lines is 2. Total number of vertices 9. Yeah. So you can already have the equation V is G3 plus G4 plus psi. You can check it, right? 9 is equal to 1 plus 0 plus 8. Now, what is the degree of divergence? Typically, we'll call it omega of G, and we work in 4 dimensions. We're just estimating degree of divergence. We don't have to regularize anything. We just want to see how bad the situation is. It is 4 times the number of loops. Right, for every loop integral you get 4 degrees of freedom, minus twice the number of internal boson lines, because every internal boson line is 1 over p squared, so that's 2 energy scales in the denominator. Right. This is the measure factor. You have 3 d4L1, d4L2, d4L3. And here you have for each internal boson line 2 powers down, is 1 over p squared. Minus a number of internal fermion lines, because they go like 1 over p slash. Right. And then there is still one more term. Who knows what it would be? Among these symbols, is there anything else that contributes to the degree of divergence? The 3 gluon vertices, because they have 1 power of momentum in them. Right? The 4 gluon vertex is not. So it's just plus G3. So that's the start. That doesn't tell you much yet. So now use the Euler identity as a topological identity. Which says the total number of loops is the number of internal boson lines plus the number of internal fermion lines minus the total number of vertices plus 1. I'll leave you to study that identity for general loop graph by itself. And we can at least test it. This was 4 plus 7, was it? Minus 9 plus 1, and that is 11, 12, 3, and that was correct. Right? So that's one thing to use. Another one is the following identity. I'll write it down first. Twice the number of internal boson lines plus the number of external boson lines is 3G3 plus 4G4 plus psi. Any sense of where that comes from?
Lines have to be divided by how many?
That's right. So you have, well, these are the types of vertices that can have boson lines coming out of them. 3 for G3 vertices, 4 for G4 vertices. And those lines coming out must either be external, E, or they must go to another vertex. And that's where you get 2 and E. And then you have similarly for the fermion, you have 2 NF plus EF is, what is the right hand side? Two psi, yes, because that 2 fermion lines come out of psi. So here are the rules, and substitute, and then you get the final answer. Omega of G is 4 minus number of external boson lines minus 3 half the number of external fermion lines, period. It's nice to appreciate this equation a little bit. So you have this very complicated graph, lots of types of vertices inside, loops, and the final answer only knows about the number of external boson lines, number of external fermion. Nothing left anymore of what goes on inside. It's almost like a holographic identity. You only have information on the outside. So that's really a nice equation. But if you have some kind of diagram, you could have taken this, you didn't need to do all this counting. You said, okay, it's a diagram with 2 fermion lines, 3 external boson lines, substitute, done. I could add this. Same story, right? So that's the superficial degree of divergence. I should warn you though, that it's not a magical formula. It just gives you the overall scaling of the diagram. It can still happen that there are subdivergences in here that are related to, say, coupling constant renormalization. So, but the overall renormalization degree of divergence you can estimate with this power counting procedure. So I'll make those remarks. Even if omega of g is smaller than 0, so not power divergent, there may be subdivergences. And this is a key element of renormalization proof, renormalization proofs. And as a previous example, we'll see something similar for the IR case. So this phenomenon of power counting is a very important tool in quantum field theory, and certainly also in QCD. So they wanted to address it a little bit. Okay. But here done for the ultraviolet case. I think by now we've concluded the UV story. So we looked at renormalization, we looked at how it works, and the counter terms, and the regularization procedure that is a necessary step towards renormalization, and some of the benefits like the RG equations for the coupling and for Green's functions. So that's the UV story, an interesting story. Certainly very important. If you haven't solved that, if you don't know how to renormalize the theory, you have no predictive power. But for QCD, it has been solved, and people know what to do. So it is not so much the most interesting part of QCD anymore. Rather, what I'd like to discuss is the infrared aspects of QCD diagrams. Not of QCD itself. I mean, the bound state physics of QCD is much less to say, much less is known. But about if you use perturbation theory, you use Feynman diagrams, not only will they have UV divergences, some will have infrared divergences, and that I'd like to go to now. So it's also these, this is the most challenging part of QCD. But as we saw before, with challenges, they lead often to new insights, new tools, and ways of knowing something about higher orders that you didn't know before. The most challenging part of perturbative QCD. So let's give a bit of an example, just to show how they occur. Let's look at this is a gluon quark vertex, and we have a vertex correction here. And momentum L goes here, here comes P1, here goes P1 plus L, and here goes P2 plus L, and here goes P2. And before we looked at what happens when L goes to infinity. Now let's look what happens when L mu and all 4 components goes to 0.
external lines are on shell.
Sorry?
External momenta are on shell.
Yeah, these are sometimes use a little bar. The fermion lines are on shell, not the gluon line, but the fermion lines. So when L mu goes to 0, let's see what happens first, and then just sketchy, and then we look immediately at a very general case, and that's actually very nice. It's called the derivation of Landau equations, and it's a beautiful bit of diagrammatic analysis. So we have P1 squared is 0. We'll assume the quarks to be massless, and P2 squared is 0 as well. It even works if they're massive, but we assume that they're massive now. So here we have L, and going P1 plus L. If L goes to 0, we certainly already have a problem here. 1 over L squared, this propagator is that's not nice, 1 over 0. But also this one, 1 over P1, this becomes slowly, this propagator 1 over P1 squared when L goes to 0. And this one goes like 1 over P2 squared. And if they're on shell, again 1 over zeros. Right, so you say, oh Jesus, that's a triple divergence. But don't forget there's also a D4L loop measure, which behaves like some angular part times L cubed dl. When L goes to 0, that helps suppress it again. So it's again a competition between the integration measure and the integrand, and to see if there's divergence or not, just like we were doing for UV. Right, so this is the situation we're facing. Almost zero energy gluon. In fact, it would be a bit more interesting even than that. Infrared, I don't only mean this. We'll see in a moment what I do mean. Okay, so you see here, at least this is another interesting issue. Let's now do a general analysis. Let's immediately do a general analysis. Since we have now a bit of experience with writing down general expressions for Feynman diagrams, and in fact, it is not, I think, not too difficult. So let's take a diagram, G, and let's write it as follows. So G, so what will G be? There will be, I won't even draw a diagram. What does a diagram have in general? There will be external lines, there's momenta coming in, there will be loops, there's loop momenta running around, there will be vertices and denominators. Every internal line will have a bit of denominator, 1 over k squared, where k squared is the momentum flowing through that line, which is typically a linear combination of loop momenta and external momenta. Here we have that also. This internal line here is a combination of an external momentum and a loop momentum. If you have 7 loops, it could be that 2 of the loop momentum flow through the same line. You can always reroute these things. All this could happen. So I have then a number of denominators, and I'll combine them all with Feynman trig. So well, let me first write them without Feynman trig. So first I have the product over L loops. We assume they're L loops. And for each of that, I have a loop momentum interval. I'll do that in d dimensions. Then, if it's a complicated diagram, there will be some huge numerator factor, which I call simply n. This will be a function of the k's and the external momenta. I'll go over the notation again in a moment. And then I have all these internal lines. That's called the total number of internal lines I. In this case, it was 3. In the previous diagram, it was many. I forget exactly how much. And each of them will have a factor kj squared plus m squared minus I epsilon. That's it, really. That's a very general expression for a diagram. Each line has a denominator. This kj here is the internal line momenta. So that would be, again, as I said, a linear combination of external and loop momenta. And some big numerator factor. Right? This is very general. I haven't given you much information other than write a typical structure. Now what I can do is combine denominators. With the Feynman trick. And then I'll get for G I minus 1 factorial product. I get now for each denominator a Feynman parameter, which I call alpha, not x, but alpha this time. So I get here integrals over the Feynman parameters from 0 to 1. Then I have the condition on all the Feynman parameters that they must sum to 1. Then I have the product of the loop momenta again, to L, d Li. My big numerator, which I just write as big N. That's all the stuff that was necessary. Right, so far, so I'm missing one thing, of course, still. That is the combined denominator. So this times alpha 1. Well, let me write it immediately in a general form. Sum from j is 1 to I, alpha j times kj squared plus m squared minus I epsilon. So I take each of these denominators with its own Feynman parameter and sum them all up. Who remembers what then the power must be? But the alphas in the problem were not these. I call the Feynman parameters here alpha. In the general formula, we have arbitrary exponents here, but we have all the exponents of 1 here. Not j, big I. Yes, big I. That's right. Minus big I. Okay, and it's really this I like. So this thing, let me call big D for denominator. And it typically will depend on the set of Feynman parameters and on the loop momenta. So you may either start with how can I ever out of such a general case draw some interesting conclusions? Well, let's try. So far I've very general setup, and the question I want to ask is when is GIR divergent? And with the word when, I mean not is it Tuesday or on Friday, I mean for which regions in the integration space of the loop momenta and the Feynman parameter integration, where in this multi-dimensional region, where are the regions where the thing is infrared divergent? So the answer is when D is unavoidably 0. Equal to 0. So not when the measure blows up, that would be the UV case, but where D, which occurs downstairs, is 0 and unavoidably so. And I'll tell you what I mean with unavoidably. Right, so when this denominator is 0, and we can provide the conditions for that. So note, D is quadratic in the Li mu variables. So these are the loop integration variables. For the ith loop has a fork momentum L mu, and in all 4 of these, so we have here for each loop momentum and each of the component of that loop momentum, D is quadratic. Because it's always a sum of momenta squared, etc. Right, so it's always quadratic. have a cubic, right? It's always a sum of squares. And linear terms as well, together with the quadratic ones. We also note that D is linear in the alpha j, in the Feynman parameters. Okay? So consider D for a given Li mu, saying of the fourth loop momentum, the third component. Then we can plot D as a function of this Li mu. Now, what behavior could it have? It's a quadratic dependence, so the typical behavior will be like this, the parabola. And of course, we're interested in the case where D can be zero. If there is no infrared divergence at all, then D can never be zero, and then I won't have that situation. But assume that there will be infrared divergences, and that we can start classifying them. So here we have two values of the loop momentum where D is zero. Right, now what does that look like in the integration plane for Li mu? Remember, all these loop momenta are complex integrals because of the I epsilon. That reminds us that for each of these things we are actually integrating in a complex space. And the loops, the two poles, will be here and there, say. Well separated. If in this situation. In that case, suppose you would have the contour passing very close to this pole and to that pole. That would be where you're in danger of having an infrared divergence, very close here and very close there. But that won't materialize because if there's no other divergence, so I can easily deform the contour well away from those poles. By Cauchy's theorem, that won't change the answer. So you as a theorist may think, it's almost an infrared divergence, but I can easily deform the contour. If there's a lot of space, no problem. So let me just write that the Li mu contour can easily be deformed away from poles. Other situation. Let me just divide this in two here. So we have the following plot for D versus Li mu. Suppose that we're in a situation where we're almost touching, or even limit, just touch the axis. Then the two zeros are almost on top of each other. And then what you get for the contour, you have two poles here and there. You cannot deform away. The contour is pinched between those two poles. Contour is pinched. And here we have a situation where D is zero and you can't avoid it. Unavoidably zero. And this must happen for all Li mu for infrared divergence to occur. Because if I can deform one away, I can make the whole D, which is after all, this one D is the sum of all terms. If one of them can be made non-zero, the whole D is non-zero. Happen for all Li mu. For the alpha j intervals, so they occur via alpha j kj squared plus m squared minus I epsilon. This is equal to 0 when either alpha j is 0, right, then the whole term is 0, 2, or if kj squared plus m squared is 0. So when that bit of line is on shell. Those are the two options. And this is known as an endpoint singularity. So here we have a situation with an infinite contour, two poles, and you can deform it away from the poles. An endpoint singularity is when you have a finite bit of interval from 0 to 1, and you can't deform the complex plane away, but if the pole migrates to the endpoint, that you cannot change. You can change anything in between, but not where the endpoint is.
These alpha j's are occur in a sum, right?
Yes. So so for each of these, either alpha j is 0 or this is 0, and if this is 0, alpha j is not 0.
For all of the values.
For each of those, either of the two can occur, but it's not that all the alpha j's are 0 or all these. They can occur depending on the term. It cannot be all 0, all the alpha j's. We'll see some explicit example in just a little bit. But so the alpha j intervals are from 0 to 1, and there you cannot avoid it if the pole is very close to the endpoint of the integration, because you can deform the contour between, but you can't escape at the endpoint. It's stuck there. So this we can, is this clear? It's not too difficult to see, it's just basic complex analysis. So we have the following conditions. So the conditions for infrared divergence, for necessary conditions. Are kj squared plus m squared is 0, or alpha sub j is 0. So that means that if either of these occurs, all these terms are 0, and big D is 0. Right? But that's not enough. We need to also encode this thing. This also we know from high school math. We also must have that the derivative on dli mu is 0 for all I mu. Right, you have exactly the situation if in the maximum the derivative is 0. This is it. These are the Landau equations. And you see how general they are. Not even that complicated. Not even that complicated to write down. So it may be good to look at an example. Is this clear so far? At least structurally, we'll look at an example and see what we get. Yeah, this one. As an example, we look at the Drell-Yan one-loop integral. Drell-Yan one-loop diagram. Essentially something we looked at before. So we have two incoming chords. Here's the incoming chord with commit to P1, L, here goes P1 plus L. Here comes P2, that's the antichord. And here goes P2 minus L. So a big D, I would write as alpha 1 D1 plus alpha 2 D2 plus alpha 3 D3, where D1 is L squared, D2 is P1 plus L squared, and D3 is P2 minus L squared. Right? So let's see what the Landau equations tell. Well, either the alpha is 0 or the d's are 0. But let's also look at the derivative condition. We only have one loop momentum, so this derivative is easy computed, and we get alpha 1 L mu plus alpha 2 L plus P1 mu minus alpha 3 P2 minus L mu. Overall factor of 2 I dropped. Right? So let's find if we can find solutions to this. Well, one solution I can think of is, I'll just give them to you. So one is, if I take L mu equal to minus z times P1 mu, and I choose alpha 3 equal to 0, and alpha minus alpha 1 z is equal to alpha 2 1 minus z. I think if you solve this, you'll find that this is exactly 0. I hope I got the signs right. So this term is 0, and if I choose L to be proportional to P1, then it's just a matter of adjusting the two alphas to get it to be 0. So note here that the solution corresponds to the loop momentum being perfectly collinear to the incoming momentum. The second solution to this equation is where this is perfectly collinear to the other incoming momentum. If I set alpha 2 equal to 0 and alpha 1 z plus alpha 3 1 minus z is 0, that's a similar solution now where the loop momentum is perfectly collinear to the incoming quark momentum. And there's a third solution where L mu is 0 and alpha 2 over alpha 1 is equal to alpha 3 over alpha 1 is 0. That's a bit of an obvious solution. You just divide the whole thing by alpha 1, keep it non-zero. But this is 0, set the alpha is equal to 0. All of these are consistent with the Landau equations. These are nice solutions, and you can immediately see also a bit of what they look like. This is a collinear solution. It's called collinear 1, collinear 2, and this is the IR or the soft solution. Collinear is that the momentum is not necessarily 0 in all its components. It's just very, very parallel to one of the incoming or outgoing momenta. And this one really has 0 in all 4 components. Okay. So we found here the solution to the Landau equations. We have two collinear singularities and one infrared singularity. We've already seen the infrared singularity when all momenta go to 0, this goes on shell, that goes on shell. If this becomes very collinear, you'll find that this propagator, both these propagators also go on shell. Because if L is equal to a non-shell momentum, 1 over L squared is also 0. So it makes some sense. Okay. Now this is nice, but it is also not so trivial to find. If I hadn't told you, this could have taken a bit of time. So if you have to do this in full generality, and so far we've been in full generality, how do you find solutions efficiently? And certainly in this way, where you just inspect the equations, imagine you have a 7-loop calculation, lots of external momenta. This will be nasty, right? And how do you get lots of equations for all these components? How do you find the solutions? Well, this comes a very beautiful, very short paper by Sidney Coleman and Norton, I forget his first name, come in. So this is the Coleman solution. So how to find most general solution. The answer is Coleman-Norton physical graphical interpretation of the Landau equations. And it's again a very nice bit of analysis. This is what Coleman was well known for. So we set m to 0. Now I already have been doing that for a while, but I ignore now. I'm looking at the QCD, all masses quarks and masses gluons. Let's ignore all the masses. So to do so, let's consider consider the term alpha j k j mu, where this is a line momentum, so a linear combination of external and loop momentum, is one term in this term dli mu. Right, there will be many terms. Let's consider such a term. Now define displacement delta xj mu, space-time displacement, by delta xj mu is some parameter lambda times alpha j kj mu. So I'm turning this bit of momentum with a mu index into a bit of space-time displacement with a mu index. By interpreting lambda I alpha j as nothing but the time component of this displacement divided by divided by the energy of that line. So I choose lambda and interpret alpha such that I think of it in those terms, and this means that I can write delta x mu as a time component times a velocity, a form velocity. This is basic special relativity. So just by choosing, having a different interpretation of the Feynman parameter times lambda, I can assign some kind of space-time displacement to this alpha j kj. At the moment it's a bit mysterious why I would do that, but I can do it. So Landau equations then say that the sum over all the displacements in a loop is 0. That's a bit of a trivial statement. The sum of all momenta going around the loop is 0. You have to come back to the same point. And if I interpret all these terms as displacements, which just says that the sum over all these displacements, whatever they will really mean, must also be 0. We'll take that fact along. Okay, so now in those terms, what do the three solutions we just had then look like? So the collinear one solution, so in those terms, go back to example. So then we have the collinear one solution, this one, where alpha 3 is 0. That means that this bit of displacement will be 0. Right? Will look like where I've drawn the line a little bit apart, but they really are on top of each other. Right? This is from the displacement from L mu, and this is from these are these two terms. This one and this one. And they must sum to 0 because it's a loop. And you can check it easily for yourself. You might want to do that in a tutorial session. So the collinear 2 solution, well, that looks very similar in this space-time picture. So I've drawn, what I'm doing now is already made an interesting step that perhaps went a bit under the radar. These lines here, these momenta, here is momentum. Now interpret these vertices as space-time positions, and the delta x's are just the delta x's between the various vertices. So I'm redrawing the Feynman diagram now, reinterpreted as a set of space-time vertices with displacements between them that correspond to the original momentum terms. So the diagram is the same, precisely corresponding to the various solutions, but now interpreted in the space-time sense. These are called reduced diagrams. They correspond to solutions of the Landau equation, well, by construction. So we already see here that off-shell lines shrink to points. In this way of, this Coleman-Norton way of interpreting the original diagram, now as a space-time diagram. Same diagram, now we reinterpret it as a space-time diagram, where the momentum terms here from the Landau equation solutions are interpreted as space-time displacements. You see, the Landau equation said either the momentum, the line is on shell, or alpha j is 0. If the momentum is off shell, then alpha j is 0, and then the displacement is 0. That's what this means. So we have here a situation of two diagrams coming from the original diagram, now interpreted as some kind of space-time sense. And what is the interpretation we can then have? Well, we have these space-time points, according to Coleman-Norton, and between them we have these delta x mu's. But the delta x mu's correspond to a time times a velocity. So it is like free propagation from this point to that point, and in between free flight with velocity here. So we can interpret this as two particles being created here, flying in parallel and then merging again. It's a space-time history of what happened. And here we could have particles splitting, flying apart and merging in, or from the other way, coming in here, splitting, flying perfectly in parallel in free flight and merging again. Right, these are the space-time interpretations of the solution of the Landau equations. And it's a perfect one-to-one match. It's a bit weird, but it's also quite beautiful. The third solution is typically drawn like this. Since it's an infrared solution, it has infinite range. Nothing shrinks to a point. So you can, it can be anywhere along the line. They're usually indicated with a dotted line or a wavy line. That's the infrared solution. Okay, so this is the interpretation. These terms in the Landau equation from the derivative, interpret them as space-time displacements corresponding to free flight between 2 points. That free flight is the displacement that you're talking about. And they correspond to the Landau equation solutions. So what is now the trick? Now turn things around. So the recipe for finding solutions is then draw all reduced diagrams keep only those that correspond, only those that represent physical scattering pictures. pictures. So let's do that for this example. So we have originally our diagram like this, and I just draw straight lines. That's our original diagram. Now I draw all possible reduced diagrams. So reduced means that you shrink lines to points corresponding to one of these alphas going to 0. Now, one thing I can do is I can shrink this line to a point. So I get this. I can also shrink this line to a point, and then I get this. I could also shrink that line to a point, and then I get a fish. Right. I can also start shrinking two lines to points. For example, I can shrink this one and this one. I get sort of a blob, a loop here, and I can have the loop there, and I can even have the loop there. And I can shrink all three lines to a point. Well then, oops, then I just get a dot here. So that's just a very stupid operation. I didn't have to think. I just shrank lines to points. And the operation is so easy. I can do this in principle to any arbitrary order. But now I have to inspect these diagrams and see which can represent classical scattering pictures. Remember, when a line begins, it must be able to fly freely without subject to a force to the next point and make physical sense. We've already seen that this makes sense. You can't have two massive particles flying in parallel. But here, you have two particles flying apart and somehow coming back together. That can't happen with free flight. But if they leave with some momentum, they will always go apart. So this cannot be a solution to the Landau equation. And these three have the same problem. This would be a particle flying around in a loop coming back. That can't happen with free propagation. It must be purely free propagation here. So neither of these are solutions. Well, this is not a solution either. This is all lines are off shell. It's not an infrared diversion situation. And there's also still in some sense, the one with 0 line shrinking to a point, that's the infrared solution. So you see, done in this way, it is much easier to solve Landau equations rather than look at steroid formulas. This is a very simple operation. Just draw diagrams and throw some away. That's when all three lines are shrunk to a point. That means that all the lines, so all the three alphas are 0. So all the line movement are off shell, and you will not have an infrared divergence. This is therefore not an infrared divergence. Okay, so this is a fairly good point to stop. Let me just make some final remarks. So this requires obviously a little bit of digesting, not because the calculations are so long, but just because it's a bit of a strange remapping of variables and a reinterpretation of what the graph signifies. But in the end, all you're after finding solutions to Landau. You're not computing the graph, but finding solutions to Landau equations. And this reinterpretation of the terms in the Landau equation in terms of the original graph or its reduced diagrams is very, very powerful. So some remarks. So the Landau equations are a necessary condition for IR divergences. So IR, I really also mean infrared and collinear. Are they also sufficient? Are they sufficient? The answer will be no, not always. In order to decide whether something that looks like a divergence according to the Landau equations is really a divergence, what would you have to do, you think? What is the general procedure you would have to do to really decide, is the diagram corresponding to one of these solutions, to when the